Hello students. Today in our first lecture of the subject signals and systems, we will be seeing few elementary concepts, classification, some elementary signals, and what a simple system will look like. So that this will be an introduction to a larger area of signals and systems that we are going to see in this subject. Good morning, friends. Today we are going to start our discussion on signals and systems. As it was mentioned earlier, signals and systems have a great importance in the field of engineering, especially in electronics and communication engineering. We are being engulfed with n number of signals, and we also know about systems which makes use of these signals to help us out in bettering the life of the mankind. So if we try to draw a simple block diagram of a system, we'll have a block diagram of this sort, which is the system, which takes in input. Normally we use X to denote input, and X of t is an input which is dependent on the time, and this input will be processed by the system to give the output Y of t. So this is an elementary block diagram of a system which is processing the signal. We have the input signal X of t, and after processing we will get an output signal Y of t. Another thing that you should keep in mind is that the t denotes time, and that too the continuous time. If we are using n, that is also time, but it is the discrete time. So if our system is dealing with a discrete signal, instead of X of n we will be using X of n, and we will be getting output. If it's a discrete output, we will be using Y of n. This is the very basic system which deals with signals. In our previous discussion, we have already introduced an elementary classification of signal, which is the continuous signal and the discrete signal. What do you mean by a continuous signal? It's very simple. For the entire time frame, the signal of our interest will have value for the entire time frame. If this is a signal, we could see for the entire time, maybe T1 to T2, for every instant you are having a value for the signal. On the other hand, for the discrete signal, we will have values only at some instances. For example, some instances you will be having values. Some discrete instances will have values. Maybe at the time 0, 1, 2, this is -1. It need not be in the positive direction itself. Maybe at time 3 it is in negative. So the discrete signal, you won't have values for the entire time, but only at some specific points you are having signal, an amplitude, a value. Naturally, all signals which is natural will be continuous. But in order to process the signal, we would convert it to discrete signals. Now, how will you convert a continuous signal to a discrete signal? That is an important process called sampling. From the continuous signal, you will be taking samples from the signal, maybe at a particular instant. These samples taken from the continuous signal will give you a discrete signal. So the first classification of signal will be based on this idea. We are having a continuous signal and a discrete signal. Next classification, the second one, the signals can be classified as deterministic signals and random signals. The signals which can be mathematically represented by an equation. Mathematical equation which can be represented by a mathematical equation. For example, a sine wave. Which is represented as, this is x of t, which is equal to a cos omega t. This is a deterministic signal. Another example is if you are having a triangular wave. which can be mathematically represented. These waves are known as the deterministic signal. Deterministic. Example for random signals are, which is a mixture of many signals, maybe. It's random in nature. If it's a signal of this sort, this is a random signal. It's actually a combination of many sine waves, maybe. But in totality, it is of random nature. So it is called random signals. So this is our second classification of signals. Signals in totality can be classified as deterministic or random signals. In previous case, it was based on continuous and deterministic signal. Similarly, another classification is possible based on its periodicity. So based on that, we can term as periodic signal and non-periodic signals. Non-periodic signals. From the name itself, it's clear. If the pattern repeats after a time period, then it is called periodic signal. And if the pattern does not repeat after a time, then it is known as the non-periodic signal. The other one is periodic. If it is repeating after a time t, which can be mathematically put as x of t plus a time period t will be same as x of t. So after every time period capital T, the same value repeats. Example is a sine wave. Sine wave is a periodic signal because it is repeating for a, it will be for a time period t, it will be this, then it again repeats the same shape. So it continues. So it's a periodic signal. Even a triangular wave is a periodic signal. A triangular wave which repeats in a time. This is the first period, repeats the second period, it continuously goes. So it's a periodic signal. The signals which doesn't repeat after a period, maybe a single pulse could be an example. Single pulse which starts there's a pulse. Or another example is a single triangular wave. Those examples comes under non-periodic signal. It stops there. It's not repeating. This is our third classification. We are having more classification which we will see in detail in our coming lectures. Now we shall move to some elementary signals, some basic signals which are available for us. First of the elementary signal is a unit step function. So we will see the few elementary signals. Elementary signals. First one is unit step signal or step function we call. The signal will be like this. On time period, there is a y-axis and x-axis, and we will have a unit signal where for the entire period the amplitude will be 1. Similar to this is a continuous signal, continuous unit step signal. Similar to this, you will have a unit step discrete signal too. If we have signals at a instance, for all amplitude will be 1. So that is the discrete counterpart of the unit step function. I will just try to draw it neatly. The next elementary function is known as the unit ramp function. Unit ramp function. You know what is a ramp? It's like a inclined climbing plane. So the unit ramp function will look like this, whose slope will be equal to 1. The slope will be equal to 1. That is unit ramp function. Its discrete counterpart will look like this. At first instant it will be 1, second instant it will be 2, third instant it will be 3. So the increase is happening in a unit of 1. So that is the discrete counterpart for the unit ramp function. Next elementary function is unit impulse function. Unit impulse function. In this case, we will have just one impulse of magnitude 1. So here we have at 0 you will have an impulse. It's a spike at the 0th position, which is at the point 0. Similar to that, the discrete counterpart is also like at 0 you will have a 1. Sorry, I'll change the color. I'll change the color and draw. 0 you are having 1. Next elementary signal is the sinusoidal signal. Sinusoidal signal. From the name itself, it will be clear to you. It's a sine wave. Sine wave, even in the discrete format, you will be having similar shape. Only thing is that it will not be continuous. Here it is continuous sine wave. Here it will be example of discrete sine wave. Next elementary signal is the exponential signal. Exponential signal. Where the signal grows or decays exponentially. If it is a growing signal, it will be like this. It will be exponentially growing to infinity. If it's decaying, it will be exponentially decaying down. I will draw the decaying also to get a clear idea for you. This is also an example of the exponential signal, but only thing is that it is decaying exponentially. It will reach zero only at infinity. Similar to this, you have the discrete exponential signal. Exponentially growing to infinity. These signals form, there are many other signals too, like rectangular pulse function, triangular pulse function. Some specific signals are also there, but these 5 could be termed as the elementary signal. And also these signals are denoted by some terminologies which is also important. Unit step function is denoted by u, and if it is continuous it will be u of t. Here it is discrete, so it is u of n. Similarly, ramp function is denoted by r of t. If it is discrete, it is r of n. Impulse function is denoted by delta. Delta of t is a continuous version of the impulse function, and delta n will be the discrete version. Similarly, any signal is denoted by x, as I have mentioned, x of t, x of n. Sine wave is being used using this general terminology. Same is the case with exponential. So this is a brief look into our signals and system, which is an introductory segment where we have seen what a elementary system will look like, and also what are the classifications that is possible for signals, and we have seen just few elementary signals.